prazer que, em nome da Comissão de Pesquisa do Instituto de Física da USP, trazemos aqui o professor Mateu Luzon, do Departamento de Física e Matemática do Instituto de Física da USP, para apresentar esse nosso último colóquio de 2020. Bom, o professor Mateu, ele possui doutorado em Física pela University of Washington, pós-doutorado em vários lugares, incluindo Santiago de Compostela, na Espanha, pós-doutorado na McGill, no Canadá.
Mateu, ele possui doutorado em Física pela University of Washington.
Atualmente, ele é professor da Universidade de São Paulo desde 2015. E em 2020, ele concluiu o processo de livre docência da Universidade de São Paulo.
Santiago de Compostela, Mateu, da comissão de prazer que, em nome da comissão de pesquisa prazer que, em nome da comissão de pesquisa de prazer que, em nome da...
Tá. Bom, só continuando, estava com feedback aqui. Então, ele trabalha atualmente com forças nucleares fortes sobre condições extremas, possui um total de 63 publicações e um índice H de 31. Tá? Então, parabéns, Mateu. Ele recentemente também publicou a Nature Physics, que é o assunto do colóquio de hoje. Obrigado. Então, Mateu, está com a palavra.
Obrigado, Adriano. Acho melhor desligar a câmera, né? Acho, talvez. Mas pode ver os slides, né?
Não, você pode manter a câmera.
Tá? Melhor, né? Como quiser. Você está mutado, mas... Ok, tá bom. Obrigado pela introdução. Eu vou falar em inglês, tá? So thank you for coming. Thank you for the invitation to give this last colloquium. So as you said, I will talk about some results of this publication. But first, some introduction. So I would like to talk about matter at very high temperatures. So just to get a feeling for how high is this temperature and what kind of physics is involved. Let's just let's go up through the temperature scales just by orders of magnitude to get this feeling of what kind of temperatures I'm talking about. So the first thing you might think of when you think it's of something hot might be boiling water, the boiling point of water. So I'll just give orders of magnitude here. Instead of 373 Kelvin, let's call it 10 squared. And this also already brings up something that would be important, is the phase transitions. So when the internal structure of some material changes as you go through some temperature change, and the thermodynamic quantities do as well. So we will see that. If we go up a little higher, another order of magnitude, so a lot higher. Every time I take a step, there will be at least one order of magnitude in temperature. You might think of something hot like a melting point of iron. Another order of magnitude, you start encountering things like this temperature at the surface of the sun. Another 2 orders of magnitude, you might have the temperature of a neutron star, for example. Another order of magnitude, another 10 times, might reach the temperature at the core of the sun. And also here's where we see temperatures that you might be able to achieve at in nuclear explosions, nuclear weapons. Maybe at a tokamak, you might get even another order of magnitude, but we're starting to reach the limit of sort of ordinary temperatures that we can achieve on Earth or even near Earth. Another couple orders of magnitude is the temperature where nucleosynthesis happens in the early universe. So this is in the early universe, this is the opposite. You start at a high temperature, and as you go lower, as you go through a temperature around this 10 to the 9, roughly, then you go from a system that is described by individual, what are called hadrons, like protons and neutrons. But at cooler temperatures, they can then start forming into nuclei. So this is a good example that will be relevant. It'll be similar to what I will talk about is, at low temperatures, you have different degrees of freedom. You can actually talk about the different nuclei and different elements that behave differently. But once you're above this temperature, it doesn't really make sense to talk about nuclei or elements. You should only talk about the individual protons and neutrons and how they interact. Another order of magnitude might reach an explosion of a supernova, but we're still not even close to the temperature that I want to talk about, which is at least a couple of orders of magnitude higher. So this is what I want to talk about is called the quark-gluon plasma. So similar to down here, the Big Bang nucleosynthesis, where the degrees of freedom change from nuclei to individual protons and neutrons. This is the point where it no longer makes sense to talk even about protons and neutrons, but instead the correct degrees of freedom to describe the system are the quarks and gluons that make up protons and neutrons. So this is the kind of temperatures above this is what I want to discuss and what I want to study. So let's see how this works. So the interactions between quarks and gluons is described by what's called the strong nuclear force or the strong interactions. So just looking now, let's think about length scales. So here's an atom which is made up of a nucleus and electrons. You can look even inside that nucleus, as we said, and the nucleus is made up of protons and neutrons. But you can even look inside the proton or neutron and see that it's made up of quarks and gluons. And the strong interactions describe the interactions between these quarks and gluons, but also it's responsible for the interactions between protons and neutrons that make up a nucleus. So we have a theory. We know what is the fundamental theory for the interactions between the quarks and gluons, the strong interactions. It's a theory called quantum chromodynamics, or QCD. It's a quantum field theory, or more specifically, a non-abelian gauge theory. So it has some similarities to, for example, electrodynamics, which you might be more familiar with. But the difference is this non-abelian gauge group that describes the interaction. So quarks interact via exchanging gluons as a force-carrying particle. But a big difference here is that both quarks and gluons are charged under this interaction, what is called a color charge, unlike photons, which do not have an electric charge. And unlike the electromagnetism, there are, this non-abelian gauge group, this SU3 gauge group is more complicated and has more degrees of freedom, let's say. So there'll be many color degrees of freedom, which will be important later. So like almost all quantum field theories, the interaction between these quarks and gluons so depends on the energy involved in the interaction. So over here is, I don't know if you can see the labels, but on the y-axis here is the coupling constant. So it's called alpha S, it's the equivalent of the fine structure constant in electromagnetism, versus energy. And as you can see, there's a dependence on energy. So for example, if you go to the left, this is approaching ordinary energy. So ordinary energies that we are used to in everyday life are even farther to the left of this plot. And as you go left to lower energies, the interaction strength increases significantly. And as a result of this, there's a property called confinement, which is basically the idea that quarks and gluons at ordinary energies don't exist as such as particles. They only exist as bound states that are neutral with respect to the strong interactions, or color neutral, or states called hadrons is the general term for these color neutral bound states. The usual simple heuristic way for explaining how this works, just intuitively, is this diagram down below, where here I have a simple hadron made of a quark and an antiquark bound state. But if we try to separate the quark and the antiquark, you need to add energy to do this, to separate them, because there's an attractive interaction between them. But as you separate them, it turns out that you end up having to add so much energy that it is actually energetically favorable. It's actually a lower energy state just to create a particle-antiparticle pair out of the vacuum. So a quark-antiquark pair can be created out of the vacuum, so that in the end you end up with two color-neutral hadrons in the end, rather than being able to. So it's not even possible to separate a quark and an antiquark and have an isolated, separated quark or gluon. So this is confinement. This is what happens ordinarily. That's why you describe ordinary physics in terms of things like protons and neutrons and their respective bound states, like nuclei or atoms, molecules, and so on. But if you go to the right on this plot, which is at higher and higher energies, you can see that the coupling gets smaller. So the interactions between the quarks and gluons becomes weaker and weaker. Eventually, at infinite energy, it goes to zero. So this means that if you take ordinary matter and heat it to a high temperature, then they will interact at a high energy. And eventually, if you go to a high enough temperature, you should break this confinement, and you should encounter a deconfined system where the quarks and gluons are now the correct degrees of freedom instead of these hadrons. This state is called the quark-gluon plasma. And as I mentioned, this is what I want to study today. As we've seen, we need an enormous temperature, a very, very high temperature to study this. So the only way that we can put enough energy into a small enough region of space is by using an accelerator or a collider. So this is what's been done for at least 20 years. There's some history before this, but the main, most of what's happened in the field started with the first purpose-built, it's called Heavy Ion Collider, or the Relativistic Heavy Ion Collider in the United States, which later was joined by the Large Hadron Collider when it turned on in 2010. It's the idea of these colliders is you take the nucleus of heavy atoms, they're called heavy ions, and you accelerate them to ultrarelativistic energies and allow them to collide in order to hopefully attain a system that is large enough so that it makes sense to talk about temperature. This is why we use heavy ions instead of elementary particles. And hopefully at a high enough temperature that it is a deconfined quark-gluon plasma where color degrees of freedom are the relevant degrees of freedom. So I will be talking about results from these experiments. Just a little bit more detail about what happens in this collision. In fact, there's a rather complex evolution of the system involving different types of physics at different scales. A major part of which is acts as a fluid, but let's go chronologically through a collision, just so we understand how it goes, and also how a collision is simulated, which this talk will also involve numerical simulations. So first, of course, you have a nucleus, which is accelerated to very high energies, which is why it looks very flat here in this picture. So one needs to know, or at least one needs to know properties of a ground state nucleus, at least the properties relevant for a very high energy collision, which happens. You have some scattering between the protons and neutrons in each of the nuclei. Before you can describe it as a relativistic fluid, there's some finite period of time, which we call we can call equilibration or pre-hydrodynamic evolution, over which time it evolves toward a state where it can be described as a relativistic viscous fluid. So the meat of a simulation is really a hydrodynamic simulation like this. And these first stages, the only aspects of these stages that are necessary are those in order to provide initial conditions for this hydrodynamic evolution. So you really only need to know a macroscopic energy momentum tensor at the beginning of this hydrodynamic evolution. This fluid evolution can describe different phases. It can describe phase transitions. So first, at the highest temperatures, there's this quark-gluon plasma phase, which is sort of the nominal material that we are interested in studying, at least today. Then as it cools down, it transitions into a system of hadrons, which can still be described as a fluid. But eventually the fluid description does break down. And you need to switch to a description in terms of particles. These individual, mostly this is made up of hadrons, which in principle can continue to scatter and evolve their momentum distributions. Before eventually they stream all the way out to detectors. And we detect these final state hadrons and their properties. And from this, we need to go backwards and infer as much as we can about what happened and the properties of the system. But of course, as I hope I'm making clear, it is a complicated evolution, and so it is a difficult task to isolate specific properties and specific physics that goes on in this evolution. You have to do modeling, so there's invariably unknown properties or parameters that you have to set from experimental data, which is what we will do in this talk. So just a quick slide. So it's been about 20 years studying this field. So actually many things have been already learned to characterize the system, the medium that's created in the system in many ways, both qualitatively and quantitatively. So I just have a slide of some journal covers. I think I should actually speed up. So the main idea is here, despite all of the progress and all of the properties of the medium that we have already determined, one thing that is still missing, or was still missing, was really a more direct confirmation that of deconfinement, that the system really is described by color degrees of freedom, by quarks and gluons, which is stated very nicely in this review article, this fairly recent review article, which lists some of the big questions that still remain in the field. And one of them is stated as the following: can we obtain an experimental determination of the temperature of the matter produced in heavy ion collision, and at the same time, its energy density? The reason this is an important question is if that's possible, then we can obtain an experimental determination of the number of thermodynamic degrees of freedom, from which we can infer the liberation of the color degrees of freedom, or quark and gluon degrees of freedom, and in a more direct sense, really confirm deconfinement. So let's talk about, just remind ourselves about the relationship between these thermodynamic degrees of freedom and the energy density, or what we will use is the entropy density. So let's recall some properties of just black body thermodynamics. So because of relativity, you can create and annihilate particles. So the particle number in a system is not necessarily conserved, particularly a relativistic system, which is always true of massless particles, but for any particles at sufficiently high temperature, such that they're ultrarelativistic. And so the number of particles, or we'll talk about the volume density of the particle number, n, depends on the temperature. So let's do a quick little hand-waving estimate. So I will, throughout this talk, I will use what are called natural units. So a system of units so that all of these constants have the value 1 in this unit system, which makes it a lot easier to write expressions, but also to do some dimensional analysis to power counting. So in these natural units, you have the same set of units for an inverse length, momentum, energy, and temperature. So from this, we can know that if the particle density is a 1 over volume, or a length to the -3 property, if there are no other scales in the system, so if we're talking about massless particles, or particles with such high temperature or energy that their mass is negligible and there are no other scales in the problem, then the density, the particle density, has to scale like t to the 3rd power, just from dimensional analysis. And the coefficient in this proportionality relation is proportional to the number of thermodynamic degrees of freedom. So let's just do a quick estimate, just quick and very dirty. Let's just assume we have Maxwell-Boltzmann statistics. Let's ignore quantum statistics. So if we have a Maxwell-Boltzmann distribution, the number density is the integral of that distribution, which of course gives us something proportional to t to the 3rd. Let's call it 0.1 pi to the -2. And each thermodynamic degree, that's for one thermodynamic degree of freedom. Each thermodynamic degree of freedom is populated independently in this idea of just a gas of massless particles. So let's count up those degrees of freedoms for what we care about, the quark and gluon system. Quarks are a spin 1/2 particle, so there are 2 spin degrees of freedom. Let's say there are 4 degrees of freedom for flavor, so up and down quarks. There are also heavier quarks, but they are relevant only if the temperature is large enough. So they're very massive, so the temperature must be large and, of order, the same order of the mass, in order for them to be created in appreciable quantities. So let's ignore them just for the moment for our hand-waving estimate. Whereas the gluons, those are a spin 1 particle, but they're massless spin 1 particle. So remember that there are only 2 polarizations, or 2 spin degrees of freedom. So if you add up the 8 plus 2, you get 10 degrees of freedom. You can multiply that, and you get an estimate of 1 t cubed for the number density. But of course, I ignored something very important here, just to illustrate a point, is that there are in fact color degrees of freedom. They are charged in this, according to the strong interactions, they have a color charge. So quarks transform in what's called the fundamental representation of SU3. So there are 3 color charges, 3 different types of colored quarks. Whereas gluons, there's 8 different colored quarks. And if we add up now, let's see, 24 plus 16, hopefully we get 40 thermodynamic degrees of freedom once we include color. So now suddenly the degrees of freedom increased by a factor of 4. The point here is really just that when you liberate the color degrees of freedom, you expect a large increase in this density. And this is why it's a signature for deconfinement. So just a little bit more. More relevant quantities for our purposes are things like the pressure, energy density, entropy density. So we can relate those all together. We can relate the pressure to the particle number, assuming ideal gas. The energy density is 3 times the pressure, which we can derive just from the virial theorem, equipartition of energy of this massless ideal gas. And finally, we have this thermodynamic identity, over which we can conclude that the entropy density is 4 times this number density that we just derived, where the entropy per particle is about 4 in this simple case. So for this quark-gluon gas, at least in this very rough estimate, you expect the entropy density to be about 16 t to the cubed. The energy density is about 12 t to the 4th. So that's what we expect. We expect a large increase, not only in the number density of quarks and gluons, but the entropy density and the energy density once you get to a high enough temperature to liberate the color degrees of freedom. So, question on this slide: can these thermodynamic quantities actually be computed from first principles? Because actually, despite the fact that we can write down the Lagrangian for quantum chromodynamics, it's very difficult to calculate many things. We can't just calculate anything we want, but this happens to be something that we can. So remember that at very, very high temperature, the coupling constant goes to 0. So at sufficiently high temperature, you can use perturbation theory and calculate these thermodynamic quantities. The problem, though, is that at temperatures closer to the transition temperature, this deconfinement transition, which is both where most of the interesting physics happens and is the temperature region that we can probe experimentally. In that region, the coupling gets very strong, gets very large, and you can no longer use perturbation theory in these temperature regions. It's a non-perturbative system, a non-perturbative problem. But luckily, it is possible, even in this strong coupling region, it's possible to compute thermodynamic quantities. You do this with numerical techniques in something that's called lattice methods, or lattice QCD in this case, since we're solving quantum chromodynamics, which the very basic idea is you take the continuum of space-time and you instead consider it as a discrete lattice, which is why it's called lattice. So you have a discrete set of space-time points, both space and time. And then you can actually solve the problem numerically and take the limit where the lattice spacing goes to 0. So this has been done. Here is the result, at least from one of the 2 groups that have done this. So here you see both the entropy density in this yellow color and the energy density in this red color as a function of temperature, here in units of MeV, which if you're not familiar with that, it's not too important, except to see very obviously that around here, somewhere around 200 MeV is where this transition, where some transition occurs. But of course, we can identify it with exactly the transition that we are interested in. At low temperatures, you see that both the energy and entropy density is very low. So we have a small number of degrees of freedom. And this is a system of these hadrons, these colorless bond states. Whereas at higher temperatures, we have this quark-gluon plasma phase, this quark-gluon phase, where the color degrees of freedom have been liberated. So you now have significantly larger density. And this transition region, which technically is not a true phase transition, but an analytic, continuous crossover. But nevertheless, there's still a fairly rapid change in phase. So we can see, so before I was just estimating the degrees of freedom, but this is a real calculation, really from QCD. And we can indeed see that deconfinement is marked by a strong increase in entropy and energy density. Today I will focus on entropy density. And the question becomes, can we confirm some of these results with heavy ion collision experiments, data from heavy ion collisions? And can we confirm that a deconfined system is created in these experiments? So this goes back to this. This is the specific question that I want to answer is, can we determine the temperature of the system? And at the same time, at that temperature, its entropy density, actually, we will use, which equivalently will still allow us to determine the equivalent number of thermodynamic degrees of freedom and potentially verify the liberation of color and deconfinement. This is the goal. So as I mentioned before, the system has a very complex, nonlinear, complicated evolution. So I want to start simple. So this is a very simple system. It's a hypothetical system, sort of a thought experiment, but it will show a lot of the relevant properties that we will need later. So it's important to realize that when we do get the final result, we are not making the assumptions made in this example, but it will help us understand in principle how it can be possible to extract some single thermodynamic relation from a system that's in principle a complicated dynamic system with non-uniform in space and time, and so on. So in this simple example, we do in fact start with a simple thermal system, uniform thermal system with some volume, V, some energy E, and some entropy S at some initial time, call it T0. And then in this example, this system then expands into the vacuum. So it's not like a water droplet like in this picture. It doesn't have a surface tension to keep it fixed. It's more like a heavy ion collision where it's allowed to expand into the vacuum. But it does so as a fluid, which is relevant to our case. Now, hydrodynamics, at least in the ideal limit, conserves not only energy, but also entropy. So the energy at the beginning is the same as the energy at any other point in time, including far into the future, and the same as the entropy. So we can reconstruct the initial thermal state as long as we have the following information. So we need these three things, but we can get it in a bit of a roundabout way, which is relevant to the actual case that we have. So if we have the final number of particles and also the energy per particle, then that gives us the final energy, which is the same as the initial energy. If we know the entropy per particle at the end, and we still know the number of particles, then of course we have the final entropy, which is the same as the initial entropy. But to completely describe the system, we would need an estimate of the initial volume. So not only final state quantities, but we need to estimate the initial volume. But the important thing here is that even if the subsequent evolution is very non-uniform, non-linear, and complicated, all we need are these quantities, these integrated quantities in the final state. And that still allows us to reconstruct a thermodynamic relationship. Okay, so hopefully that gives us a little bit idea of how things will work in a more realistic case. Next, what I want to do is argue that it's natural for there to be a relation between a temperature of the system and the mean momentum, or specifically here, the mean transverse momentum. So here, PT is the component of momentum perpendicular to the colliding beam axis. And so there's this idea from way back in 1982, back when the superproton synchrotron was running at CERN, proton-antiproton collisions. The idea here is that this mean transverse, the average of this transverse momentum of all the particles, should be a fraction of the energy per particle. It should be related to the energy per particle, and the temperature should be a measure of the energy per particle. And so suggested that there should be this proportionality between the mean transverse momentum of particles and a temperature. And the number of particles should be proportional to the entropy. If there's a fixed volume, then it's also proportional to the entropy density. So the idea of this paper was if you vary the collision energy and make a plot of the mean transverse momentum versus the multiplicity, or the number of particles. Here, CH is the charged number of charged particles. which is what's easier to measure compared to all particles, then that should give you the dependence of the temperature as a function of entropy density. Okay, so that turns out to be too simplistic and with questionable relevance, applicability to these proton-antiproton collisions at lower energies. But it does give us some good starting points that this, especially this relation here that relate the mean transverse momentum to a temperature is something that we would like to do. But how about some of the complications? What are some of the differences? So in a heavy ion collision, we don't have actually an isolated system. Or I mean, it is, the entire system is an isolated system, but what we observe is not the entire system. We observe some slice of the fluid near the center. And so in this slice that we observe, the energy is not conserved. It actually decreases as the system expands due to the work done by the pressure. Early on, you just have this fast longitudinal expansion. So the energy of this slice of the fluid decreases like t to the time to the 1/3 power. But later on, the transverse expansion sets in. So in this transverse direction, it starts to expand and the pressure decreases. So then eventually, or actually fairly quickly, the energy converges to some final value, asymptotes to a final value. So this now this mean transverse momentum corresponds to something related to the final energy and entropy. A little bit different than Van Ho's idea. Okay, so finally, let's start our analysis. So first, I want to define something called an effective temperature and effective volume, which is the following. So it is, we calculate the total energy in this slice of the fluid and the total entropy at the very end of the system. So, oops, this is a typo. This should say freeze out. So once the particles have stopped interacting, they're frozen out. At that point, you can integrate over the system at some freeze out surface, which might be a constant time or something more complicated. You can calculate the total energy and the total entropy at the end of the system evolution. Now, these effective temperature and volume are the temperature and volume of a uniform fluid at rest with this same energy and entropy. So you can just solve this equation. So there's a single thermodynamic system with this energy and entropy. It has some temperature and some effective volume according to these relations. And I emphasize that this is a definition. So there's no non-trivial physics that we've seen yet. It's just a definition. And these temperatures and these volumes don't necessarily correspond to the temperature, for example, at some specific point in the evolution of the system that we're pointing to. These are just definitions of some effective temperature and volume. But I intend to show that we can actually extract these defined quantities, the temperature and the entropy density at that temperature from experimental data. And this is the goal. Okay, so with these definitions in hand, we can perform numerous simulations varying in different parameters. For example, an important unknown parameters, I mean, roughly known, but unknown within some range is, for example, the viscosity of the fluid. So these lines, for example, correspond to ideal hydrodynamic limit plus different values. So this dashed line has only shear viscosity and this dotted line has shear viscosity and bulk viscosity. But the idea is really just to vary these parameters to get a range of behavior that we can understand. And so first we can calculate this effective temperature, which, as I said, is a defined quantity. So it's perfectly well defined. In a simulation, we can just calculate it. And then in these same simulations. So let's see. So this is the effective temperature, and on the x-axis is the centrality. So over the left, these are very central collisions, sort of very head-on, and these are more peripheral collisions with these nuclei. We also calculated the mean transverse momentum of these final surviving particles. So this is something that can be measured more directly, or very directly. And as you may have already noticed, there's a very strong correlation between them. In fact, they're very, to a very good approximation, they are proportional to each other. Just like this idea from a long time ago that there's this relationship between the mean transverse momentum and the temperature of the system. And this observation is the main key to all of the results, I would say. It's very non-trivial. The definition of the temperature and the volume is just a definition, but this relation is a discovered relation that we find only by doing simulations. But you can see that even though the temperature and therefore the mean PT change with viscosity and various other parameters, this relationship remains. The mean PT still is very accurately described just by this 3.07 times the effective temperature. It's valid for different centralities of the collision. It's insensitive to the parameters, uncertain aspects of the system. Okay, so therefore we can, since this mean transverse momentum can be measured in experiment, you can just get a value. So for example, in 5% most central collisions, you get some number like this. And we can directly extract a temperature, this effective temperature that we defined, which is about 222 MeV, or about 2 times 10 to the 12th Kelvin. This uncertainty, for those that care, is mostly determined by changing what's called the freeze-up temperature, which is where the point where the particles stop interacting. Okay, so we have a temperature, which doesn't really give us much yet, since this is just a theoretically defined quantity and not particularly interesting by itself. What we still need is the entropy density at this temperature. So let's try that. So the entropy density is the total entropy over the effective volume. If we know the entropy per particle, as in that earlier simple example, and it turns out that we do, there's a very nice extraction of this from this analysis from 2019. The number of particles, the number of charged hadrons is measured. And so therefore we know the total entropy at the final, at the end of the system. And the main problem, the main source of uncertainty in this is that the effective volume is not a measured quantity at all. So we must estimate this from theory or from some model. So what we find, which is very useful, is that if we calculate the initial transverse size of the system, which is a model-dependent quantity, but if we calculate this initial transverse size, the effective volume, which again is something defined that we calculate in a simulation, turns out that these are proportional. The effective volume is proportional to the cube of this transverse size. And moreover, this transverse size in the most central collisions can be estimated by the radius of the incoming nuclei. So since we know the radius of the nucleus from low energy scattering experiments, from that we can get the initial transverse size, and therefore we can estimate this effective volume. So that's how this works. And so from all of this, we can now calculate the entropy over volume in these central collisions, the same one where we got this temperature. and we get this result. So 20 units of entropy per cubic femtometer. And where this relative uncertainty is a bit larger, see about 40% of that uncertainty we attribute to an uncertainty in this initial size R0, and about 60% of the uncertainty comes from the uncertainty in the transport coefficients, which gives you an uncertainty in this relation here. Let's see. We're doing better on time than I expected. Okay, so that's the main results of the entire colloquium. So, well, let's see. Oh yeah, so we want to compare actually. So we have the result. So we found this effective temperature and this entropy density. So now let's compare it to these first principles computation. So we can, like in this plot, we can divide by the temperature cubed, in which case we get a result like this. And remember, this is the entropy density, so you should compare to this yellow line here. And the result is like this. And so we can see that, first of all, it's compatible with the first principles calculation. And despite the significant uncertainty, we can very clearly see that there is a large number of degrees of freedom, and that the color degrees of freedom have been liberated. It is not compatible with a colorless system of hadrons, which has a much smaller entropy density. And so we have indeed confirmed that a truly deconfined quark-gluon system is created in these heavy ion collisions. Okay. So that's the main result, but let's do a little bit more from these same calculations. Let's see what happens if we change the collision energy of these collisions. So this was done, these previous results I wrote down somewhere, were done in these lead-lead collisions at the LHC at 5 TeV per nucleon pair. But what happens if we change the collision energy? So here on the x-axis, instead of collision energy, we write the multiplicity, but still to the right corresponds to higher collision energy, and to the left corresponds to lower collision energy. And you can see how some of these quantities change. So you can see that the effective temperature increases with collision energy. No big surprise. And the effective volume is essentially constant. So when you increase the collision energy, you're basically heating the system at a constant volume. If we look at mean transverse momentum, we can see that it still very closely follows the effective temperature. Put them together here. Here you can see the specific collision energies that correspond to these multiplicities. And at all energies, at all relevant energies, the deviations from this scaling with the mean transverse momentum with the temperature is essentially negligible. So now we can use this to probe more thermodynamic relations, specifically the speed of sound. So the speed of sound is defined this way. So the variation of the pressure with respect to energy density, which we can relate by thermodynamic relations to a variation of the temperature with entropy density. So it's proportional to a logarithmic derivative of the temperature with respect to entropy density. But now we can use these relations that we found, in particular that the temperature, this effective temperature is proportional to the mean transverse momentum, and the entropy density is proportional to the multiplicity, the charged hadron multiplicity per unit rapidity here. And so we can relate the speed of sound to a logarithmic derivative of the mean transverse momentum with respect to multiplicity. And the nice thing here is that the proportionality coefficients cancel out in this ratio. Or just more physically speaking, so increasing the collision energy means as I said in the previous slide, putting more energy into a fixed volume. So this gives us direct access to the compressibility of the system, which gives us exactly the speed of sound. If we analyze data here, we used these 2 points here at 2 different collision energies at the same facility, the LHC, to obtain this particular value for the speed of sound of the system at this effective temperature. So the speed of sound of the quark-gluon plasma, we now know, at this effective temperature. Whereas this uncertainty here is mostly from the uncertainty in the effective volume. And so now I've added a little inset here with the speed of sound, which is also calculated from first principles in this red band here. And this little bar is our result, which we can see also agrees with the first principles calculation. Okay, with that, I think I can just summarize. So the basic, most important points are that it is indeed possible to reconstruct the thermodynamics of strong interactions in this range between 200 to 220 MeV using experimental data from relativistic heavy ion collisions, specifically the measured mean transverse momentum and the measured multiplicity, or the number of particles. The results agree with first principles calculation obtained from Lattice QCD methods, and confirm that a deconfined quark-gluon plasma is produced in the collision, where color degrees of freedom are in fact liberated. Okay, thank you.
Sorry, okay, let me just take this. Thank you very much. I would like to invite everybody to unmute the sounds to virtually. Yeah. Okay, so now we can start the questions. That was a very, very interesting seminar. Then, I mean, you went to a place that I never thought it would exist. I mean, so deep and so the thermodynamics in such a high temperature, high energy level. It's really amazing, and it's really completely. It was completely out of my mind, and now I can see. So it's open for questions. So, Matteo, I would like to understand. I mean, you went from let's say classical thermodynamic principles, mix up with quantum chromodynamics, and then you went to a kind of a new style of thermodynamics. Is it possible to have a feedback? So do you have a feedback on the classical thermodynamics? I mean, so how it works, this path going in one way, and if it's possible to go backwards?
Well, I'm not sure I quite understand what you mean. So I mean, all of the thermodynamics that happen at the very end in the actual analysis are really quantum. It's a quantum system, quantum chromodynamics. You can compute it with Lattice QCD, and you do it in experiment. These are definitely quantum systems with the usual thermodynamics from a quantum system. I mean, a lot of the introduction about counting degrees of freedom is classical and very hand wavy. But just to give you an idea of why you get such a strong increase in entropy density and things like this. So yeah, I'm not sure I quite understand the the question. I don't know if you want to rephrase or if I should just try to answer anyway.
No, it's like I understand that you are in a quantum level, and my question is the theory you developed, you are developing, or you are in this group of development of this quantum chromodynamics, thermodynamics. If we learn what we learn on that level, is it anything that can be sent back to other levels? Like
well, let's see. I mean, it's a very unique system. You know, there aren't very many, I guess, other non-abelian gauge theories that are useful. Well, maybe in some dense matter systems. Mostly here, I think the really non-trivial important things are things that I didn't even do. Just the fact that it's strong coupling in these strongly interacting systems, you can compute these thermodynamic quantities using lattice methods, which is not my work. Maybe I wasn't very clear about what's my work and what's not. So these lattice results here are not my work. My work is these phenomenology results, extracting information from experiment. And a lot of this phenomenology is very unique to this collision system. It's very special that we have this specific relation between this, that we can define this global temperature even in a very non-uniform dynamic system, and that it has such a strong relationship to this mean transverse momentum, which makes sense intuitively, but it is still a very special property that isn't going to be true in any general case. So I don't know if I can think of any very good examples of where these results would be very useful in other fields, but I will think about it.
Okay, I have one question that just this come up from YouTube. The first is from Tiago. It asking, hot strong interaction means something else?
So yeah, it's a little bit confusing because these QCD, the quantum chromodynamics, describes some interactions that we just call the strong interactions, which can be a little vague. Instead of saying strong nuclear force, strong nuclear interactions, it's very common just to say the strong interactions. And it's confusing also because the strong interactions are not always strong. So if you go to extremely high energies, which you of course rarely see, but if you do go to extremely high energies, then the coupling is weak and the interactions are actually weak. So I think probably that's what this question was about, is what does it mean, these strong interactions? And it, in different contexts, it can mean different things. But for me in my field, it usually just means quantum chromodynamics and the interactions between quarks and gluons.
I have one more question, actually two more from YouTube. The second one is from Fabio Canedo. He asked, hi, Matteo, great presentation. It is possible to generalize this method to different B? If yes, then how?
That is an excellent question. So, so all of this was done assuming that the baryon chemical potential is 0, which is a pretty good approximation for these highest energy collisions. But in the field, it is also very interesting to study what happens when you lower the collision energy a bit, which increases the baryon chemical potential. You have to take into account the non-zero baryon density, the density of baryon, net baryons. And the question is really, I think, about these lower energy collisions that are done to map out more of the phase diagram, and there might be a critical point and so on. And the question is, can we extract the thermodynamics or equation of state of the system at a finite baryon number? And the answer is, I don't know. I think we would have to do a lot of simulations to see whether we can still find very simple relationships like this, which My guess is that we can't, because there's another variable involved. So now you have a larger, functional space, your parameter space. And so it probably would be difficult, but you would have to verify. Perhaps even in that case, it's possible that we can make a connection between a temperature and some mean transversal momentum measurement. But there's another degree of freedom, which is the net baryon number, which probably has to be taken into account. So it's an excellent question, but I don't have a very good answer. We would have to study it, and I'm not sure whether it will be possible. You're muted still.
Yeah, I just realized. Okay, Fabio just said thank you. So I have another question from Cristiano Oliveira. He said, hi, Cristiano. Okay, nice talk. It is possible to use results from astrophysics and combine it to some of the predictions from your theory? I ask this because at so-called Big Bang, we would have a similar soap you are investigating with your theory.
Yes,
actually, Cristiano is right there.
Yes. It's also a very good question. So indeed, in the early universe, the temperature is high enough to have this quark-gluon plasma. And it really is somewhat similar conditions. So certainly the equation of state is important, and also even transport coefficients might be important. So I think at this stage, people who simulate the early universe cosmology don't take into account things like possible viscosity, which either means it's not important or it hasn't been studied. I'm not sure which is the case. So at least right now, from everything that I've looked at in astrophysical, or at least cosmological studies, I haven't seen any results that we could use. But perhaps our results can be used in cosmological results, because we are quickly becoming more quantitative in our determination of thermodynamic relations like this, and also transport coefficients. So my hope is, yeah, someday that we can still collaborate and feed down maybe the other direction. That's for cosmology. There are also astrophysical applications, possibly. So there may not be any astrophysical systems that reach these high temperatures, but there might be. So, for example, these neutron star mergers, which are very important these days, because you get the gravitational wave signatures from them. In these mergers, you might have a high enough temperature to have a deconfined system. And these systems are at much larger density. So this is related to Fabio's question about finite chemical potential. So it's a little bit different and involves a little bit more different parts of the phase diagram. But I do also have hopes that these two fields can intersect. But at the moment, I don't know of any specific results that we can use, or specific results of ours that can be directly implemented right now in astrophysics. But in the future, I hope so.
Well, I know that we have one more question from YouTube. But out there, the guy just raised the hand, and I'm waiting the question be formulated to send back, then I can pass to you. Let's see. Okay. It's actually from Fabio again. So in my understanding, the confined phase at RHIC was already a consensus in the community. Could you emphasize the difference between your confinement confirmation and previous one?
Yes. So the consensus, as far as I understand it, which I hopefully do, is that the required energy density that we expect to be required for a quark-gluon plasma is attained in these collisions. And they can be very well described in these hydrodynamic simulations. So it behaves as a fluid, and that means that it can be described with a temperature, in a statistical thermal way. Even if it's not really thermal equilibrium, it's close enough that you can talk about temperatures and phases. So by deduction, then you have a system that has a high enough temperature that's higher than the deconfinement temperature, and so you should have a deconfined quark-gluon plasma. But I'm not aware of a direct probe of really the deconfinement itself. Like are the degrees of freedom necessarily quarks and gluons, or could it be something else? So of course we expect it to be, because that's what QCD predicts. But this work is really just a more direct confirmation of what really are the degrees of freedom for sure, and it's more direct confirmation of deconfinement, even though we had a very good idea before, just because we expect a system at that temperature must be deconfined.
Adriano, there are people waiting here in Zoom for questions. Are you going to take those, or?
Sorry.
There are in the participant list, you can see the people with the raised hands. There's Edivaldo, Lucas, and Fernando.
Yeah. I didn't see Fernando with raised hand. Is it? Oh,
yeah.
Let's.
We've been waiting for a while.
Oh my God! Oh my God! Sorry, I was Fernando. Sorry, I was looking. I was not looking the place where I see the raised hands. Sorry. So Fernando, please.
I think that Edivaldo should go first.
Oh yeah, I didn't see the list coming up. I just saw that now that the three hands up at the same time. So then go, Edivaldo, please.
Okay. Thanks. Thanks, Max, for Matt, for the very nice talk. So it was very clear. You made something very complicated and understandable, I would say. So my question is around slide 18 and 19, you defined this effective energy and entropy. And if I'm correct, you said that these are effective quantities, right? Defined at an effective temperature. And then, correct me if I'm wrong, you mentioned that this cannot be directly associated to the temperature at a particular point of the fluid. So my question is, how can I interpret this temperature and energy and entropy, and how do I compare with the lattice QCD calculations? So are you comparing the same thing? So I don't know if the question is.
Yes, I mean, yeah, it's a little bit complicated to explain. So, so these quantities are definitely not. You can't point to a particular point in the system where they occur, at least by assumption. Okay, you can go backwards now that we see how it works and relate them probably to the system at some earlier time. But even within these definitions, I mean, let's see. Within the definition of these quantities are actual thermodynamic relations. So when we get the entropy density at this temperature, that is the thermodynamic relation of QCD. Because when we obtain these values, so in a simulation, we really know the thermodynamics because we put it in by hand. And so when we calculate the energy and entropy, in order to get these quantities, we need to use the thermodynamics that we used in the simulation. So that sounds circular, but what we of course do is then change the equation of state in the simulation and verify that everything still works the same way, which was an important part of the analysis. So because of what we found in our simulations, we found that we can in fact extract these things from the energy and the entropy and an estimate of the volume of the system. So I guess, I mean, there is some assumption that this effective volume is related to the actual volume of the system at earlier times. But I believe, I mean, based on all of the checks we did, we do in fact believe that the results should be compared directly to the thermodynamic relation computed from first principles. But I don't know if I explained it very well.
No, it's okay. I got it. Thank you.
There's somehow a thermodynamic relation implicit into these definitions, and since we show that we have the relationship between these things that we expect, you know, as long as the consistency checks work, then they are in fact correct thermodynamic relations.
Okay, so I'm not sure which one is the next, if it's Lucas or Navarra, because I didn't see the, so Lucas, could you?
Hello, Matthew. Can you hear me well?
Yes.
Can you understand?
Yes.
So I loved the results from the presentation. I knew them from last week, and when I saw the opportunities to see you speak, I came here. So I'd like to know why weren't made some energy measurements in different energy ranges, only on 200 MeV, 220 MeVs.
Why not? Temperature.
Yeah, temperature measurements in different energy range. Yes, why weren't they made yet?
So to do this, we need results at different collision energy. So at least using this method, it's only in a single type of collision. You could only extract a single effective temperature by construction of this. So to get the temperature dependence, you need different collision energies. There are some. If I go away to the end somewhere, you have, for example, these two energies at the LHC and this one at the relativistic heavy ion collider. So we definitely could do the same analysis at these two energies, but it turns out the temperature is almost the same at both. I mean, the energy is not different. So remember, the energy goes like T to the 4th, or the energy density. So that you don't really get a different temperature range here. At RIC, the data are not ideal for this. So we could try to do an extraction anyway, but what we preferred was to make a plea in the paper to have data from these experiments, since they're still running and analyzing results that are comparable to the way the data was taken from here. So in the future, we should be able to do this at 200 MeV collision energy, which should give you a temperature that is, oh, let me think. I mean, all that does is reduce the temperature by about 20%, I think. So it still does not give us a big difference. And considering the error bars in our results, you know, we could move down by about 20% and get something around here. But to get a wide range of temperatures, we need to have a larger range of collision energy. And at each collision energy, we would need to verify that all of this works the same way, that all of these relations hold up the same way, which is not something that you know, is proven from first principles. This is something that is a result of doing many simulations.
Experimentally, we would need collisions not from lead to do in bigger energy range.
Yeah, most of the energy range is the important thing. A different size of a collision, so different nucleus, actually does not change the temperature. We have this also in the same paper. Here we do collisions of different size nuclei, but it's probing the same temperature. So really, the collision energy is what's important for changing the temperature.
Yes. Okay, thank you.
Okay, so
And finally, Fernando Navarra, please.
Thank you. So thanks for the nice talk. I have first this very general question, which is what's your best argument to be sure that you are dealing with a thermal system? How can you be sure that the system is in thermal equilibrium? I know there's a lot of papers and arguments about that. I just want to know your personal view on this. To me, it seems that you cannot, you can never be sure that you're dealing with a thermal system just by looking at the PT distribution of the particles, because it's possible to go to a different system like E plus, E minus, where you have a collision at high energies and you produce a lot of particles, and you look at these particles, at the transverse momentum of these particles, and they follow a Boltzmann-like distribution, and you can adjust and fit it and extract a temperature. But this temperature doesn't mean anything. It's just something that you still have to understand. But the system is small, you're really sure that there is nothing in thermal equilibrium. There may be some other mechanism responsible for this thermal looking shape. In heavy ions, you really believe that you have time, energy, and probably temperature and energy density to produce a thermal system. But I just wonder, why are you convinced about that? So to me, personal experience, you need some other argument that you haven't mentioned in your talk, which is something like the elliptic flow analysis or other things that you can measure in heavy ion collisions that taken together, they make you think that you are talking about a thermal system, but not just because you look at the PT distribution and you extract a temperature. Do you agree with that?
Yes, 100%. So this result relies on the assumption that you can describe the system as a fluid, with a fluid dynamic, and you need outside evidence beyond this work in order to convince yourself that that is an appropriate description. So it is not inherent to this thing. I 100%, you can't just look at the momentum distribution of the final particles in a system like this and conclude that the system is in equilibrium or close to equilibrium. I don't know if you want more. I think you just wanted to know whether I agreed, or should I keep expanding?
No, that's fine. That's fine. I'm happy with that.
Okay.
Okay. Any other question? So, since no more question, I would like to invite everybody to unmute the microphones.
Only one more question. Can I ask?
Okay, so
Yeah.
yes, of course.
Matthew, about the velocity of sound, why isn't there unity on the 0.24?
Yeah, so as I mentioned at the beginning, so I always use this the system of units where the speed of light is 1. So for example, anytime you have a speed like the speed of sound, this number is always in units of the speed of light. So this this means is about 0.24, or about 1/4 of the speed of light is, well, actually this is speed of sound squared. So this is 0.24 times the speed of light squared. Is what this means. You always have to put the units in back at the end to get the more conventional SI units.
I forgot the natural unit. Thank you.
But in this case, this is just this number times the speed of light squared.
Okay. Okay. All right. So then now I would like to invite everybody to unmute the microphones. To acknowledge, okay. Thank you, Matthew, very much. Thank you, everybody. Okay.
Thank you.